In our last video, we learned about how to use the binomial expansion triangle to more quickly expand binomials. So things like a plus b raised to the 10th power. This is a great example. If you had something that was raised to the 10th power, it's going to take you a while to get to the 10th row of that binomial expansion triangle. So what we're learning today is this thing called the binomial expansion theorem, which is effectively a shortcut to our shortcut. But in order to do that, we're going to need sort of a new piece of notation, a new notation. And so we're going to learn that now. So here it is. There's this thing called the combinatorial coefficient. In some books, it's denoted NCR, but IB, in a lot of the work that they do, instead uses this notation over here, this idea of like an N over an R sort of in parentheses. I'm not going to get really deep into what this means. We'll talk about it a little bit later, but for now, I just want to sort of practice doing this thing. So the idea is, when you're doing this combinatorial coefficient, the number that's on the top, you've got this number on the top and the number on the bottom. That top number you're going to factorial here, the bottom number you'll factorial here, and then you'll take the difference between the two numbers, n and r, and put that factorial here. That's exactly why in sort of yesterday's practice I had you guys sort of compute the division of factorials. So I've got two examples of these here. Let's go ahead and try those out and make sure you guys have got this down. So in this example, I'm going to ask you guys to compute the combinatorial coefficient for 8,3 and for 7,2. So pause the video, try 8,3, and then come back to us and take a look at what we've got here. So according to the formula we had on the previous page, this 8,3 would be 8 factorial in the numerator, and then in the denominator 3 factorial, and then 8 minus 3, that would be 5 factorial. So something you're going to notice here, by the way, is that when you're computing these combinatorial coefficients, these two numbers on the bottom are always going to add up to the number that's on the top. So that's always the way these combinatorial coefficients are going to work out. So the way that we practiced doing this in sort of yesterday's, red lesson was that, you can sort of see this as 8, 7, 6, 5, 4, 3, 2, 1 in the numerator. And then in the denominator, we'll have our 3, 2, 1 and our 5, 4, 3, 2, 1. Okay, and again, as we practiced yesterday, the 5, 4, 3, 2, 1 will cancel out on both of these. And then we just need to look and see where we can get the rest of this stuff to cancel out. It looks like the 3 times 2 will take out the 6. And so all we're going to have left is this 8 times 7, which is 56. Okay, so hopefully you got that one. If you haven't already done the combinatorial coefficient for 7 and 2, go ahead and pause the video and do that one now. So when we do 7, 2, we will have 7 factorial over 2 factorial, 5 factorial. Similarly here, 7, 6, 5, 4, 3, 2, 1. The 2, 1 from the 2 factorial and the 5, 4, 3, 2, 1 here. These pieces will cancel out here. All I'm left with is the 7 times 6 on the top and the 2 on the bottom. The 2 can reduce the 6 down to a 3, and I'm left with 7 times 3, which is 21. So these combinatorial coefficients are really pretty quick to compute, and this is how we do it. Now, I don't think I could get through this video without spending some amount of time talking about what these things mean. And eventually I am going to connect it back to the binomial expansion triangle, but our next question is sort of like, what do these things mean? Very briefly, this combinatorial coefficient nr is going to give you the number of ways that you can choose r things out of n options. And this is a little bit sort of general right now, so I'd like to look at a specific example. Notably, I'd like to look at this. What does that thing mean? Right, so in the last example, we found that the combinatorial coefficient for 7, 2 is 21. What does that mean? Well, according to the previous thing, what this would mean is it would mean out of 7 objects, if we got to choose 2, how many ways could we choose them? So, imagine, if you will, that you had numbers, you had objects 1, 2, 3, 4, 5, 6, 7. We might wonder, how many ways could I choose 2 of these numbers? Well, I could do 1 and 2, or 1 and 3, or 1 and 4, 1 and 5, 1 and 6, 1 and 7. Those are all the ways that I could do it while choosing 1. Then I could do 2 and 3, 2 and 4, 2 and 5, 2 and 6, 2 and 7. I could do 3 and 4, 3 and 5, 3 and 6, 3 and 7. I don't know if you guys want to hear me say all of those numbers, but right here I sort of made a list of all of the different ways that I could could choose two of these objects out of here. And if we look at this, there are sort of how many ways were there that we could do all of this? It looks like there were 6 of them here, 5 of them here, 4 of them here, 3 of them here, 1 here. This is 11 here. There's another 7 ways here and another 3 here. Those are 10. Sure enough, there were 21 ways that I could choose 2 objects out of these things. So I know that this slide was a little bit messy here, but I wanted you guys to sort of see this really worked out. This combinatorial coefficient, 7, 2 being 21, means that if I have 7 objects to choose from, and I only get to pick 2 of them, there are 21 ways that that could be done. I would like to spend more time talking about what this means, but we need a lot more practice with this stuff first. So for now, I'm going to ask you guys to kind of be patient. We will come back to this idea and we will talk about it more in the future. So now it's time for us to take this and connect it to the binomial expansion triangle. So I want you to consider these factorial expressions, and if you did the assignment from yesterday, you'll recognize these. These were things that we did in the assignment yesterday. So I want to encourage you guys, look back at the work that you did from yesterday, and see what answers you got for these things, and write them down. So these are the numbers that you should have gotten when you did all of these problems yesterday. I hope now you recognize, hey, this thing here is basically the combinatorial coefficient 7, 7. And this one here is the combinatorial coefficient 7, 6. And this is 7, 5. And this one is 7, 4. And this one's 7, 3, 7, 2, 7, 1, and finally 7, 0. Now the next thing I'd like to ask you to do is I'd like you to write out up to the 7th full row of the binomial expansion triangle. And I want you to see what you notice. So here it is. It turns out that the binomial expansion triangle, while it has all of its own cool patterns within itself, the binomial expansion triangle basically is full of these combinatorial coefficients, right? This 7th full row here is full of all of the combinatorial coefficients that have a 7 on the top. This first one here is 7, 7. This one here is 7, 6. This one's 7, 5. This one's 7, 4. 7, 3. 7, 2. 7, 1, and 7, 0. Now what this means for us in practice is that if we play our cards right, if we learn what the connection is here, we don't have to draw the binomial expansion triangle anymore. Instead, we can use these combinatorial coefficients to sort of jump quickly to the exact spot that we need in order to work through our problem. And so that's what we're going to look at and figure out next. So rather than explain to you sort of exactly how to connect these combinatorial coefficients with the binomial expansion triangle, what I think I'd rather do is go through something called the binomial expansion theorem. The binomial expansion theorem is sort of complicated when we write it out in a purely precisely mathematical way, but the idea is simply when you have something like a plus b that's raised to the nth power and you try and expand it out, every single one of those terms will have a format just like this. It'll have the combinatorial coefficient that's in the front. This is the thing that we used to get from the binomial expansion triangle, but now we'll get it from, our new formula. It will have the first term raised up to a power, and it'll have the second term raised up to the rest of the power. Okay? So here's the important things to know. N will always be the power that your binomial was raised up to. Okay, so if this is an 11th power thing, like if somebody's saying raise this thing to 11th, N will always be 11. Okay? R is the power that you want to raise your first term up to, and then n minus r ends up being the power, you don't really get to choose it, it's the power that you're forced to raise the second term up to. And the reason that I say forced is that second term, that this n minus r, is always going to be sort of the rest of the number that's left. So for instance, if we're working with a situation where n is 7, and I need r to be 2, automatically that n minus r is going to be 5. It's going to be the other part of the number that lets me get my complete 7. So anytime we're doing these problems, I want you guys to remember that there's always going to be your combinatorial coefficient, there's your first term raised to a power, and there's your second term raised to the rest of the power that we have left. The rest of this video is just going to be me going through 3 different examples. They're going to start out fairly easy, and they'll get a little bit more complicated as we get toward the end. All right, so here's our first example. Find the coefficient of x to the 12th power in the expansion of x minus 5 to the 13th power. I wanted to start with one that's, on the one hand, simple with the binomial expansion theorem, but would be really frustrating to have to use the triangle for. I, for one, really don't want to have to go down to the 13th row in that expansion triangle. I mean, it's neat to see the patterns and everything, but like no thank you. So the idea here is, I know that the terms in this thing are all going to have three parts. The first part is going to be that combinatorial coefficient that we talked about. The next part is going to be the first term raised to some power that we're going to have to figure out. And then there will be the second term raised to a power that we're going to have to figure out. And so when I personally work through these, I usually sort of start here in the middle, right? They wanted me to find something that was an x to the 12th. That means I'm going to have to raise x to the 12th power. Okay, but if I'm raising x to the 12th power, what power am I forced to use for the negative 5? One way to do it is we know this other power is supposed to be n minus r. N is 13, that's the power we're supposed to raise this thing up to. R is the 12, the number we used over there, we get 1. Hey, yay, that's 1. You can do it this way. You can also look at it and know for yourself, these things have to add up to 13. So if I use 12 here, I'm going to have to use 1 over here. The last thing we do is we fill in this combinatorial coefficient, right? It's 13 on the top because that's the power that I'm raising this thing up to. And it's 12 on the bottom because that's the power that I'm using for this first term here. Just to mention it, you could also have put 1 down here because it doesn't matter which one of these things you use. The formula is going to wind up being the same thing. Our next step here is computing this combinatorial coefficient. According to the formula we learned earlier, it's going to be 13 factorial over 12 factorial 1 factorial. And hopefully you guys are getting the hang of simplifying these things. The 13 factorial and the 12 factorial is really going to simplify all the way down to just being 13. So this is going to be 13 x to the 12th times negative 5. And then all I have to do is multiply these two number pieces together. That looks like it's going to be negative 65 x to the 12th power. And so the answer to my question, find the coefficient, negative 65. Okay. We got through this problem really quickly, relatively speaking, because we didn't have to go down to the 13th row of the binomial expansion triangle. Let's look at a couple more examples. I mentioned that the difficulty in these problems was going to ramp up a little bit, and so here we go. Find the coefficient of x in the expansion of this thing. So the first thing I want us to recognize is that we already know what the structure of this answer is going to be. It's going to have a combinatorial coefficient. It's going to have 2x squared raised to some power. And it's going to have negative 1 over x raised to some power. And as I think about it, there's actually one more thing I can fill in here. Because this is raised up to an 8th power, this up here has to be an 8. So the real question for us winds up being, what are these things going to be? What powers do I have to use here in order for me to get an output of just x? At this point, I personally like to employ a little bit of kind of like guess and check here. I look at it and then I think to myself, these two powers are going to have to add up to 8, because that's kind of the way that this thing works, right? Whatever number I get put here, when I apply it here, it's going to get doubled. And when I put a power here, it's going to get multiplied with the negative 1 power that's here. So if I'm only supposed to have 1 power of x left, this one's going to have to be kind of bigger to cancel out the size of this one that goes here, right? So I'm going to start with a guess, right? I'm going to say, let's see what happens when r is 2. If I use an r value of 2, I would get 2x squared, and then negative 1 over x raised to the, well, now think about it. If I were to put a 2 here, what power would have to go here? That would be 6, right? Well, when I do that, I'm going to get 4x to the 4th times 1 over x to the 6th. I don't even need to finish this line of thinking. It's really clear that these things, these are going to cancel out, but it's certainly not going to give me the x that I have left. I made my r value too small. Let's try r being 3 now. If I did that, I would get 2x squared cubed times negative 1 over x raised to the 5th power. Let's see here. That would give me 8x to the 6th times negative 1 over x to the 5th. Hey, there it is, right? I've got 6 x's on top here, 5 x's on the bottom. Those are going to cancel out and leave me with just this x. Now that I figured that out, I can tell this is supposed to be a 3, this is supposed to be a 5, and so we'll put a 3 down here. There are some ways to sort of compute that and find it precisely, and I might share this at some point later. For now, I would encourage you guys to sort of think about and try those numbers and figure out the things that are going to work. Now that I've got these pieces here, I can go through and do the computation for the rest of this. Right? If you haven't already finished the rest of this problem on your own, sort of pause the video and make sure that you know how to do at least the computation of the rest of this process. So this 8, 3 combinatorial coefficient will be 8 factorial over 3 factorial, 5 factorial. The 5 factorial is going to cancel the 8 factorial down to just being 8, 7, 6. And the 3 factorial would be 3 times 2. Those will take out the 6 and leave me with 56. Okay, so I'll have 56 from this. I'll have 8x to the 6th from this. And then over here, I'll have negative 1 over x to the 5th. As I predicted before, this x to the 5th and the 6th, they're going to drop out. So we'll have just our x. Now we have to do 56 times 8. That looks like that's 448. And we still have this negative from over here. So again, to answer the question, finding the coefficient of x, the coefficient would be negative 448. Okay? So in cases where you're working with something that's a little bit more complicated here, you often have to do some thinking over on the side to figure out what powers are going to work for this. All right, so here I have another example for us, and this one has another sort of different thing that you might sometimes see. This one is going to ask for find the constant term. Now, what the constant term means is it means the term that has no x in it. Which means that when I do the expansion of this thing, there's probably going to be some place where all of the x's cancel out. So just like we did in the previous problem, I want you guys to remember and recognize there's going to be a combinatorial coefficient, there's going to be 5x cubed raised to some power, there's going to be 2 over x raised to some power, and what I need is somehow for all of those x's to cancel out. So I'd like to ask you guys to pause the video, try this one on your own. If you feel like you're still a little bit stuck, I would get you to remember, we know this is supposed to be a 4 up here, and you know that these two powers up here are supposed to add up to 4. So think about what you would put into these things in order to get all of these x's to cancel out. So it seems to me that the thing that's going to work is for me to put a 1 here, because that would sort of give me x cubed from here. And if I used all 3 of the rest of my powers over here, that would mean this is going to give me over x cubed, so all the x's are going to cancel out. That means I'll put a 1 down here, and now we just need to go through the computation. This combinatorial coefficient will be 4 factorial over 1 factorial, 3 factorial. The 3 and the 4 factorial drop you down to just 4, so you get 4 for that. Here you're going to get 5x cubed, and here we'll get 8 over x cubed. Nobody is surprised when the x cubeds cancel out. The 4 times 5 gives me 20, and 20 times the 8 I had from over there is 160. And there it is. We found the constant term in this expansion. This expansion has a total of 5 terms. One of them doesn't have any x's in it, and that one term that doesn't have any x's in it is 160. So I hope that you guys are seeing at the end of this video how we can use combinatorial coefficients and the binomial expansion theorem to figure out how to do these binomial expansion problems even faster than we did when we used the binomial expansion triangle. So I hope that all made sense and that the practice problems you guys have all go well for you.